Hello everyone. This lesson is going to go over some different types of questions that you can encounter dealing with compound interest, and these are questions where you'd have to isolate other variables besides the a variable in the formula. So here's a question that they often will call a present value question. What is present value? Present value is defined as how much you'd have to invest now in order to end up with a certain amount later, which is basically just isolating p in the compound interest equation. But some books actually turn that variable into PV, and they'll turn the variable for a into FV, standing for future value. So you just need to know, and I'll write both of those formulas in a second. So here's an example of the style of question you might see. How much would you have to invest today at 3% compounded monthly in order to have $10,000 in 15 years? So a lot of the issues with these questions is being able to recognize what did they actually give you by reading the question. If I'm saying how much would you have to invest today, that means we don't know our original investment. So our principal, let me just write the formula here actually before we start. So this is the regular formula for compound interest. And what I was saying with the PV and the FV, some textbooks will actually write this like this instead. Now, I don't like this version simply because for students who might struggle with mathematics, this looks like two variables. So does this, and that can throw people off. So I would rather just use the original formula, a is equal to p times 1 plus I to the n, and get students to understand that p is your principal, which is your present value, and a is your future value, the one that you're going to end up with, your final amount, in other words. But you do need to know that both of those versions are possible. So we'll just move that one off to the side. So we're going to use the a equation. Let's write out our knowns. So our givens, we know that our final amount, A, is $10,000. That's what we want to have at the end of 15 years. We have to calculate our I and our N. So I is the interest rate per compounding period. So the interest rate is 3% monthly, which means I have to divide that by 12. That's 0.03 divided by 12. And if I pull up my calculator here, that gives 0.0025. My N value is how many interest payments am I going to have over the life of the loan? Well, in 1 year, if it's compounded monthly, I'm going to have 12 of them, but I'm going for 15 years. So I'm going to multiply 15 by 12 to find out how many payments of interest I'm going to have overall. 15 times 12 is 180. What is my unknown? Well, this time I don't know my principal. So I have to rewrite the equation to get the principal all by itself. That's actually quite easy. If I have a is equal to p times 1 plus I to the n, and I'm trying to get p by itself, I just have to bring this bracket over to the other side. Well, that bracket is multiplying, so it ends up being a over 1 plus I to the n. Now again, to get you ready for certain things that other textbooks will do, because this used to be hard to typeset, one of the alternatives to writing it to write the equation, which I don't like a lot, but I'm going to show you anyway, is like this. P is equal to a times 1 plus I to the negative n. When we have a fractional scenario, the denominator of the fraction can be moved up and written as a negative exponent. But the only reason mathematically, actually it's not even a mathematical reason, the only reason aesthetically that I think people would want to do that is because you're rewriting it all on one line, without having to write it as a fraction. And that might have been necessary when typesetting stuff would have been difficult to do, but nowadays with computers there's no issue, so I think that this is a much better way of writing that formula. Now, we really should be isolating p on the left, so I'm just going to move that over like that. And now we can substitute all of our values in. So we've got our a, which is 10,000, divided by 1 plus 0.0025, all to the power of 180. And I'll pull up my calculator and show you how I would type that in. So this is an older style calculator where I have to do things a little bit backwards sometimes, but I think I can do this one exactly as it's stated. So let me just start fresh here. So we've got 10,000 divided by bracket 1 plus 0.025. Ooh, I forgot a 0 there. I'm just going to backspace 0.25, close the bracket, to the power of 180. And if I look in my window here, I can see that that's written the right way, and when I press equals, I get $6,379.86. Did I remember those properly? Just gonna double check. Yes, that is correct. Therefore, because this is a word problem, we should have a sentence. The amount that needs to be invested today is $6,379.86, and that means that we would end up with $10,000 in 15 years. All right, so that's the first type of question that you will have to isolate variables for. These are called present value questions, and it's just getting used to the way that they're written. What happens if I ask you to isolate for time? Now, the time value in compound interest scenarios is hiding inside of the n variable. So here's an example. How long will it take for a $1,000 investment to gain $20.50 in interest at 4% compounded monthly? So as soon as you see a how long question, that is a time value. Time is hiding inside of n, and I'll explain that a little bit later. We're going to isolate n first. Well, actually, I can explain it now. If we go back one slide, look at where the time value came into play. The 15 years was right here, right? So that's why it's hiding inside of an n. So start foreshadowing what we're going to have to do. How are we going to pull the time out? If we got our n value by multiplying by 12, hint, hint. So let's list what we have. So if we're taking $1,000 investment, that's our principal, and we're gaining $20.50. Now that's the interest amount, but not our little I. We need to calculate our final amount by adding that to the 1,000. So they're trying to trick you here. They're giving you an extra step to do. But if you understand the idea of gaining interest on an investment to get a final amount of money, you should be able to figure out that you just add 1,000 plus 20.50 to get your A value. Our I is going to be a calculation that we're going to have to do, so I'm just going to do that right here. I is equal to 4% compounded monthly. That's divided by 12. So 0.04 divided by 12, and I believe that's 0.0025. I'm just going to double check that to make absolutely sure. Oh, I've gotten rid of my calculator. Let's bring that back. So 0.04 divided by 12 is, oh, I was wrong. Well, good that I checked. 0.0033. So let me fix that. Got ahead of myself there. All right. And we are rounding that off, which is going to cause a little bit of an issue, but it's not so bad. So we're just going to leave it like that. And our n value we don't know. So let's write our equation out, and then we'll see what we have to do to isolate n. Now normally I tell my students to, I'm going to run out of room here. Let me move this next example down. So normally I would tell my students to not substitute values in until you're ready to isolate the variable. We can do that a little bit here. So if we're trying to isolate n, we're going to do a divided by p equals 1 plus I to the n. But now it'll actually make a little bit more sense if I start putting the numbers in. So our final amount was 1020.50. Our original amount was 1000. Our I is 0.0033 to the power of n. Now to save some space, I'm just going to write over here. So this is an easy division to do. We can do this one in our head, right? We're just moving the decimal place 3 spots to the left, so 1.0205. And we can add the 1 plus 0.0033 as well, so that's 1.0033 to the power of n. And we have to now isolate an exponent. So to isolate an exponent, we need the anti-function to an exponential, and that anti-function is a logarithm. So we're going to log both sides. Don't have a lot of room here. You know what? I'll just do. Oh, of course that would happen. Let's just move everything over a little bit. Give us a little bit more room. Okay, so log of 1.0033 to the power of n. And what that does, what I like to call the down in front rule, is it moves the exponent down in front of this equation. So we end up with log of 1.0205. Let me just put a bracket around here. Equals n times log of 1.0033. And because this is now a multiplication, I can isolate n by bringing log of 1.0033 underneath and dividing, but rearranging to get n on the left, that's going to give us log of 1.0205 divided by log of 1.0033. And that's going to give us our n value, but we're not going to be done yet. I really should have put that next question on the next slide, but anyway. So let's do our logarithm calculation. Here's our log button on this calculator. So on this calculator, I have to put the number in first. So 1.0205 log divided by 1.0033 log. And you can see that that's the correct division right here. And I'm going to press equals. And that gives 6.159, which I could just round to probably 6.2. That's our n value. But n is not time. N is time times the compounding frequency. And in this case, the compounding frequency was 12 because it's monthly. So to rearrange to get time all by itself, I'm going to have to divide n by the compounding frequency, which we normally multiply by with n. All right, but it's because we're isolating the time value. So n is 6.2. Our compounding frequency is 12. This is approximately 0.5. Let's see what it actually is. So it's 0.52 approximately years. So that means that basically in about 6 months at 4% interest compounded monthly, $1,000 is going to have gained $20.50. So I'm going to make this note a little bit nicer, I'm going to move that next question to the next slide as quickly as I can here. I use the arrow. Cut. Paste. How long would it take for $10,000 to double that 4% compounded daily? So here's another example that's looking for a how long. So this one's looking for time as well. Now we're starting at $10,000, but we're asking it to double. So remember that $10,000 is our principal, but we need our final amount. Well, if $10,000 is doubling, that's not hard to figure out. That's just $20,000. We need to calculate our I. 4% compounded daily. Daily is 365 days per year. So 0.04 divided by 365. And sometimes when you're working with such small numbers, folks, you might have to expect to end up with scientific notation answer, but we'll see what happens on this calculator. So 0.04 divided by 365. Yeah, so see, I was expecting a scientific notation answer, and sure enough, e to the negative 4. So this answer is 1.095 times 10 to the negative 4. Now that just means move the decimal place 4 spots to the left. So 0.000195 is my daily interest. Very small value compared to 0.04, but it's because we're dividing it by 365. So, and we don't know our n value. So substituting everything into my formula again. So I'm going to isolate and substitute at the same time. So I'm going to bring the p over and divide, but I'm going to replace the a by 20,000, the p by 10,000, 1 plus, and that's going to be 1.001095 because you're just adding 1 plus I, right? And because this is a doubling question, and we've seen doubling questions in a previous lesson, your ratio is always going to be 2 when you're doubling. So if you were tripling, you would end up with a 3 there. And I'm going to leave a little bit of room here because we know what's coming up. I have to logarithm both sides again. So that's going to bring the n down in front. Right here. So let's combine a few steps here. If the n comes down in front, that means the log of this number is going to come and divide underneath log 2. So we can directly isolate n by dividing all of that, like so. And let's see what we get on our calculator. So log 2, so on this calculator I have to press 2 first and then log, divided by 1.000195 log equals, oops, I forgot that number, 6,330.5. 6,330.5. Seems like a really big number, but remember this is n, and n is equal to time times the compounding frequency. We're isolating time, so that means divide n by the compounding frequency. Our n is 6,330.5. Our compounding frequency is 365 because it's daily. So 6,330.5 divided by 365 is going to give us 17.3 years. So it'll take approximately 17 years to double $10,000 to $20,000 if the interest rate is 4%. And remember that these are simple compound interest scenarios, meaning we're just putting money in the bank, walking away. So this could be a GIC or a savings bond, some sort of investment that is, a one-time drop-in amount of money, walk away, come back and see what's there afterwards. All right, one more type of scenario. The only variable we haven't isolated yet is I. So we're looking for the interest rate, but the interest rate is hiding inside of I. So we have to isolate I to find the interest rate. So what interest rate will make $2,500 become $3,000 in 10 years if it is compounded quarterly? It's very similar to the previous example, except this time it's N that we know and I that we don't know. So what is our principal? Well, we invested $2,500. Our final amount is going to be $3,000. Notice that the final amount is always greater than the invested amount, right? Our N value, if we're doing 10 years compounded quarterly, we get 4 payments a year times 10 years. So that's going to be 40 payments of interest. Looking at our formula again, we're isolating for I this time. So we're going to get to the point where we have I almost by itself. Let's put our numbers in. So we're going to have A divided by P. So 3,000 divided by 2,500 equals 1 plus I to the power of 40. So what's 3,000 divided by 2,500? That gives 1.2. How do we isolate I? Well, as I often tell my students, if you don't know the math to isolate a question, a variable in a question, make the question easier, but something you're more familiar with. So we need a variable with a power equal to a number. So if I gave you, as an aside, x squared is equal to 5, what would you do? Well, you would square root both sides to get 5. Now a square root has a little 2 hiding here for the type of root. And we've seen in previous lessons that we can do the root of any power. So what we need to do here is the 40th root of both sides. But instead of doing the 40th root, which some people can't do on their calculator, we're going to use the exponent version of a radical, which is a rational exponent, a fractional exponent of 1 over 40. And that's what we're going to do to both sides. I'm going to use a different color to highlight that. On this side, if we do a fractional exponent of 1 over 40, all that we're going to have is the argument 1 plus I that's going to come out of there. So isolating for I is going to require us to subtract 1. Let's get that written out, and then we'll use our calculator to find the final answer, all right? So we're going to have 1.2 to the power of 1 over 40 minus 1. So I'll take out my calculator. Let's clear this all out so we have a fresh start. So we're going to do 1.2 to the power of bracket 1 divided by 40. So you do have to put a bracket around the exponent. Notice that I didn't put a bracket around the 1.2. I didn't need one because it's the only thing being raised to that power, but I absolutely needed a bracket around the 1 divided by 40. Minus 1, and that gives us 0.004. approximately. Let me just double check that. Yes. Oh, it's actually 4.6. If we round that off, it's actually 4.6. Okay? But we're not done. This is not the interest rate. This is the interest per compounding period. I is usually equal to the rate divided by the compounding frequency. So we need to re-isolate R. That means R is going to be equal to I times the compounding frequency. In this case, the compounding frequency was quarterly. So we're going to do 0.0046 times 4. So 0.0046 times 4 equals 0.0184. However, we usually write the rate as a percentage. So if I take 0.0184 and multiply it by 100%, that's going to give me 1.84%. And the interest rate that we were looking for is 1.84%. And now you've seen an example of every type of scenario where we have to isolate a variable dealing with compound interest. So let's just recap all of that stuff. So the very first one we did was a present value question. Present value is simply isolating the p in the compound interest question. The second type we did was isolating for time, which actually requires us to isolate for n. And because n is an exponent, we're going to have to use a logarithm to pull that exponent down in front. Once we've done that, we have the extra issue of understanding that your n value contains time, but it's time times the compounding frequency, meaning we have to divide by the compounding frequency to be able to get our final amount in years. For this one, it was the exact same one as the previous one, so I'm just going to skip that one. The last type is what happens if we're looking for the interest rate. Well, interest rate is hiding inside of the I of the equation. So we isolated for I, and to do that we have to use a root that matches the exponent. So this case was a 40th root, but instead of writing it as a root, which a lot of calculators can't do, we wrote it as a fractional exponent, which every calculator can do. You have to subtract by 1 to get I by itself. And then we have a similar issue to n, where we have to remember that I is equal to the rate divided by the compounding frequency. We have to undo that division, therefore multiply by the compounding frequency, and then you really should write the answer as a percentage instead of a decimal, so we just multiplied by 100% to get our final answer. And that's it for that lesson. That shows you an example of every kind of question you might encounter. All that's left to do now is to practice and make sure you're comfortable with the language and the questions. So have yourselves a great day, folks. We'll talk to you soon.